All right. Hi, year 11s. This is Mr. Lim again here, and this is another special request about how this components go through chromatography columns or things like that, and how their speed varies. Okay, so remember, chromatography, you're passing things through a stationary phase, and so that's all these little balls here. This is the stationary phase. Okay, and effectively you've got a mobile phase, which is effectively all of that area there, which I'm not going to shade in. Okay, so the mobile phase is that stuff around the stationary phase. Mobile phase, which also flows through the column. Okay, so the stationary phase and the mobile phase has the components go through them. I'm going to use little X's or stars or something to show these components going through them. Now, as these components go through, they can attach to these little stationary beads or whatever they are. Right? And if they attach to them, those stationary phases, then they're going to stop, for all intents and purposes, going through the column, and assuming they're going through that way. All right? So if they stop there, they're going to slow down. So they're going to attach on, but then they might disconnect. Okay, so they might disconnect, and then they start flowing again. All right, so they might flow again. Right, I might show the path of maybe just one little thing going through. Okay, so this little particle is flowing here, flowing there, then flowing here, then it gets stuck again over here. Right, and it gets stuck. Okay, so it might stop again. Right, and then it will flow again, flow again, flow again, and it might get stuck over here. Right, so the idea is that the more times it gets stuck, the slower it's going to be. And the point is that what's going to determine whether it gets stuck or not? Well, it's going to be the relative polarity of the molecule versus the polarity of the stationary phase. All right, so effectively, if the molecule has high binding affinity to the stationary phase, which is effectively meaning that it's going to get stuck to the stationary phase, right, then it will be slower. Move slower through column. And so the idea is that what determines whether it has a high binding affinity to the stationary phase or the mobile phase, right? So effectively, if the stationary phase and the component match, then they're going to have a high binding affinity. So if stationary phase matches component, that leads to high affinity, which means that it's going to go slower. Okay, so that's what determines the speed of the substance through the chromatogram column. Okay, so let's go through a couple of examples. So here's another two columns. Okay, let's just say that the red is polar, stationary phase, and the blue is non-polar. Okay, whether they match those polar or non-polar stationary phases determines whether they go through it quickly or not. Okay, and let's say that this green particle is non-polar, and this yellow particle is polar. Okay, so let's track the progress of these two things here. So the green non-polar particle is going through a polar column, which means a polar stationary phase, which means that it's not going to stick onto it very often. So it's going to go here, go here, go here, and go here, and then get stuck. Right? Then it's going to continue going on, once it gets unstuck, going on, and then it's going to get stuck here. Then it's going to go on and go on. So the green one has less affinity to the stationary phase, and so therefore moves through quickly. Okay, so the green one has a less affinity to the stationary phase because they don't match, and therefore it moves through quickly, meaning that it will have a high RF. Yep, high RF or low RT. Okay, and if you don't remember what RF and RT is, you're going to have to look those things up. RF is the retardation factor and RT is the retention time. Okay, but let's have a look at what happens with the yellow one. Okay, the yellow one is a polar molecule, and it's going through a polar stationary phase, which means that here it's going to go here, and then it's going to get stuck, and then it's going to go here, and then it's going to get stuck. Then it's going to go here, and then it's going to get stuck. And every time it gets stuck, it stops moving, which means it's going to go through this thing quite slowly, because every time that it touches one of these things here, it's going to get stuck. And since it sticks onto it so often, it means that it has a high affinity to the stationary phase, thus takes longer to pass through, which means that it's going to have a high or a low RF. It means it's going to have a low RF or a high RT. Okay, so whether it matches or not. So let's go put this same thing through the non-polar stationary phase. What do you think is going to happen with the non-polar component? Okay, it's going to, the green non-polar component is going to have a high or low RF and a high or low RT. Okay, so it's going to stick to it a lot, right? The non-polar is going to stick to the non-polar stationary phase a lot, which means it's going to have a high affinity, which means it's going to have a low RF and a high RT. But the polar molecule is going to have low affinity to the non-polar stationary phase, and so therefore it's going to have a high RF and a low RT. Okay, so the yellow one has a low affinity to stationary phase and high affinity to the mobile phase. Right, and the green one has a high affinity to stat phase. All right, so one more little thing to go through. Let's have a look at what this will look like in terms of chromatograms. Okay, so here I say that my stat phase is polar and my mobile phase is effectively non-polar. Okay, I have my origin here, I have my solvent front here, okay, and I have three components. I have component A, component B, component C. Okay, so this A, it moved the furthest, which means that it probably didn't stick to the stationary phase very often. So this has low affinity to stat phase, which means that it will be non-polar because it won't match the stationary phase, which is polar. Okay, so it will not match the stationary phase, which is polar. Right? However, this component C here took a long time to go through because it hasn't gone through as far. It keeps on getting stuck, which means that it is likely to be a polar component because it's going to be stuck so often, and so therefore it's going to have a high affinity to stationary phase. High affinity to stat phase. All right, one last one. Let's go through a chromatogram where it's a gas chromatography or a HPLC, something like that. Okay, where we have the little spikes. Okay, so remember what goes on here, time, what goes up here, something like absorbance or something, right? We have four components, A, B, C, and D, right? Remember that the one that came out last is effectively very slow, which means it has a high affinity to a stat phase, right? And the one that came out first has very fast, which has a low affinity to stat phase, right? And so therefore, if I say that A is polar and D is non-polar, you should be able to work out what the various phases are, the stat phase and the mobile phase. Okay, so if A is polar and A has a low affinity to the stationary phase, it means it will not match the stationary phase. So therefore, it's going to be non-polar stationary phase. D, being non-polar, was very slow and had a high affinity to the stationary phase, which means that it is very polar. Sorry, wait, what? Yeah, mobile phase. Yeah, high affinity to the stationary phase. Therefore, the mobile phase must be polar. Okay, so that's the concept of speed going through chromatograms. Hope that helped. Adios.